Hello everyone, welcome back to week 2. In this week, we'll be looking at sorting, searching, and greedy algorithms. So, the first problem for this week, which illustrates why sorting is required, is AUTICI, which is a Koki problem. And this is the first actual Olympiad in informatics problem which we are looking at. So, as with all OI problems, we will be going subtask by subtask, and I'll be explaining the solution for each of the three subtasks in this problem. So in this problem, we are given n friends who have garages in which their remote control toy car is stored. We need to connect all the garages together by choosing two indices A and B, choosing two different friends A and B, and joining them together. So the cost for joining two friends A and B is dA plus dB, where di is the length of the road paths in the ith friends pack. And we need to basically ensure that each and every friend is connected. So we need to ensure that D1, D2, D3 all the way up till Dn, all of them are connected together. And we need to find the minimum cost or the minimum total road length or the minimum total sum of the values of Di plus Dj when we are joining I and J in the optimal network, in the network in which all the garages are connected. So let's take an example. Let's say that there's only one friend and the value of D1 is 10. Then clearly we don't need to connect any garages because there's only one friend who's already connected. So we'll print 0, which is the correct output for the first example. In the next example, when we have three friends 5, 5, 5, then it's clear that we can choose, it doesn't matter which pair of friends we choose to connect. We can connect the friends 1 and 2, and then we can connect 2 and 3. So the cost will be 1 and 2 cost is 5 plus 5, and 2 and 3 cost is 5 plus 5. So the total cost is 20. Now, in general, let's look at the first subtask where all the DI values are equal, because that's the second example. So when all the DI values are equal, which is the first subtask, we know that we can connect all the pairs of friends in any order. It doesn't matter what order we connect them in. And that's why let's just say that we're connecting 1 to 2, then 2 to 3, then 3 to 4, and all the way up till n to n minus 1 to n. So n minus 1 to n. So in this case, the total cost will be d1 plus d2, and we know that d1 and d2 are equal, plus d2 plus d3 plus d3 plus d4, and all the way up till dn minus 1 plus dn. So we can write this code very simply, and this takes O of n time. And we know that this is the cost because we have to add the costs for connecting each pair of garages, and we are connecting n minus 1 pairs of garages to make sure that all the n people are connected. So in this manner, we can find out the total cost for subtask 1, and we'll just print this expression. Now let's consider the next example, which is subtask 2 or subtask 3. So in the next example, where we have the elements 7, 3, 3, 5, the costs are not equal, they are different. So over here, the strategy may slightly be different. We need to consider an optimal method to connect all the garages. So we know that one possible method is to do what I just said, to connect 1 to 2, 2 to 3, 3 to 4. So that will give a cost of 10 plus 6 plus 8, which is 24, which is not optimal. There is a better solution. And the reason why this is not optimal is because all the costs, all the DI values are not equal. When they are all equal, it doesn't matter which stuff you connect together. But when they are unequal, obviously it matters. So let's consider what is optimal. In this case, it's actually optimal to connect 2 with 1, 2 with 3, and 2 with 4. So to connect the second guy or the second person, his garage, with the garages 1, 3, and 4, and this gives a cost. This gives a cost which is equal to 3 plus 7 plus 3 plus 3 plus 3 plus 5, which is going to be equal to 12 plus 12, which is again 24. So actually, the connecting 1 to 2, 2 to 3, and 3 to 4 was also optimal, and this was also optimal. But if you consider another example where you consider the numbers to be something like 1, 2, 3, and 4, for example, then if you just connect the adjacent values, if you connect 1 plus 2 and then 2 plus 3 and then uh, and then 3 plus 4, you will get a cost of 15. And in this case, it's actually more optimal to connect the nodes, the values in this manner. And let's take another example. In this example also, we get that the cost is 14. So 14 is better than 15. 14, the total sum of the road paths, the total sum of the lengths is 14, which is less than 15. And you can take many other examples as well in which the values are different from each other. And you will see that just connecting them together in a straight line doesn't work. And it's actually more optimal to choose the smallest person. So now I'll be explaining the key idea which is required for this for the full solution. So the full solution relies on a greedy strategy. Notice that the cost when you take two elements together is di plus dj, and let's say you want to connect, you have connected the cars I and j. Now you want to connect another car which is possibly some other value k. You want to connect that with I or j. Now the key idea is that the cost would be, if you connect it with I, the cost will be di plus dk, versus if you connect it with j. So if you connect it with I, this is the cost, and if you connect it with j, the cost will be di plus dj. So the same cost for connecting I and j, but you're connecting dj plus dk. So in this case, you can see that you're connecting the car K, the person K with the person J. You're connecting those two garages together, and it's clear that the only difference in these two sides of the expression are di versus dj. So it's clear that it will be more optimal to choose whichever is smaller. So if di is less than dj, we go with di. Otherwise, we go with dj. And now once we have connected the k value, so let's say that di is less than dj, then it's clear that this one will be more optimal, and we'll connect k to di. Similarly, if you consider another one, which is, let's say one more value needs to be added. Let's say we get another person who we need to connect to the garage, DL for example. Then it's clear that we will choose the minimum of these three people, whichever value of di or dj or dk is smallest, and we'll connect that dl with the min of these three. So the min of these three plus dl will be the cost for adding dl as well. And in general, you can see that it's always optimal to choose the smallest element and to keep adding the edge, or to keep connecting the smallest element with the garages of the other elements. And this is the greedy idea for the solution. So the full solution will basically rely on, the first step is finding the min di. So let x equal to the min di. Then we know that we should connect this value of di. So let's say that di, or let's say let pos equal to I, such that di is the min, d pos is the min. Let pos be the index, such that b of pos is the minimum element in the whole array. Then we know that we should connect, the optimal strategy will rely in connecting pos with 1, with 2, with 3, and all the way up till with n, except for pause, of course. So this is the key strategy and this is the key greedy idea. The reason behind why the greedy idea works is this example. When choosing between adding the garage K to garage I or J, we will choose the smaller garage. We'll choose the garage with the smaller DI value. And that's why in this case as well, we will just start with the smallest pause and we'll connect all the other garages to pause. And that's why the cost will be equal to D1 plus D pause plus D2 plus D pause plus all the way up till Dn plus D pause. Of course, we need to subtract out the value of D pause plus D pause because we are not connecting pause with itself. So we need to like remove the value of D pause plus D pause. And one way to write this would be we just do the sum of all di, for I going from 1 to n, and then we add pause n minus 1 times, so n minus 1 times d pause, where d pause is the minimum value of di, so you can write it as n minus 1 times min bi for all I going from 1 to n. So this is the O of 1 expression or O of n expression for finding the final answer, and it's as simple as this. And the reason behind why this is true is the greedy idea of connecting the smallest element with all the other elements. So now I'll show you the code which implements the same idea. So in the code, we will take in the value of n, the number of garages which we need to connect together. We will take the sum as log because the values of vi can be up to 10 power of 9 and it will overflow, the sum will overflow if we don't use it long. Then we will take all the values of di from 1 to n and we will sort. So this is the inbuilt sort operation. In a future video, we will see how we can pass a third parameter as well, which is called the comparator parameter, and we can sort the elements in the order by which we want to. So in this case, the order in which we are sorting is just from smallest to largest. However, if you wanted to sort it from largest to smallest, you could just change the comparator over here, and this will actually sort it by largest to smallest. So this is the default comparator where you just return x less than y. However, for more complicated problems, as we'll see later, we need to use a custom comparator for sorting. And then we realize that we just need to add up all the elements from 1 to n. So another way to write this would be to just go for all I going from 1 to n. We just do sum plus equals to di. And we will take the smallest element as well. So we'll add all the elements and add the smallest element. So n minus 1 times d of 1. Because d is sorted, this implies that d of 1 is the smallest element. And hence we will add n minus 1 times the smallest element. And now I'll just submit this code to see that it gets accepted. So there was a small error in the operation or in the expression which I wrote. You should have realized that it should be the sum of all elements plus n minus 2 times d of 1, because it's not n minus 1, it's n minus 2, because we are already counting d of I when we are summing up all the elements. So already once it's getting counted over here. So we need to count it only n minus 2 times, because over here it appears n minus 1 times and it's appearing, it should appear n minus 2 times over here plus once, which is n minus 1 times in total. And now when I make that small change to the code, it gets accepted. So I hope you understood this greedy idea which was used for solving this Croatian problem. I hope you like this solution. If you have any doubts, do leave them in the comments down below. And if you like this video, don't forget to give it a thumbs up. Thank you.